Hi everyone, in this video we're going to revise rates of reaction and enthalpy changes through past paper questions. And you can find this pack of past paper questions using the link below in the description. The first question, Boltzmann distributions show a gas at two different temperatures. Which Boltzmann shows the dotted curve at a higher temperature? A Boltzmann distribution shows the spread of kinetic energies of gases, and when we increase the temperature, the curve shifts to the right and flattens. So if we look at all the choices, it has to be A. Next question is about enthalpy changes. We have a reversible reaction and it's asking us to draw an enthalpy profile diagram for it. So it started us off, it's given us the axes and the reactants. If we look at the delta H, it's an endothermic reaction, which means products must be higher energy than reactants. And it's asking us to label activation energies without a catalyst and with a catalyst. So here we do our activation barrier and we label it EA. And the arrow must always point up because energy is needed. And here we've got a lower activation energy required when using a catalyst, and we can label that EC. And our delta H, it's an endothermic reaction, so our arrow has to point up because it's a positive delta H. And here is where we get our marks. So the first mark is for drawing our products above the reactants with the delta H arrow labelled correctly and pointing upwards. The second mark is for either activation energy or activation energy with a catalyst labelled correctly, and the third mark is for both of those activation energies without and with a catalyst labelled correctly. The next question is a practical based question about rates of reaction, and we have a graph and we have to join the points and it's a best fit curve. So draw a best fit curve, so we join the points, nice smooth curve. Use the graph to determine rate of reaction at 50 seconds. So using our ruler, let's find 50 seconds. We draw a tangent to the curve at 50 and then do change in y divided by change in x to get our rate. I came out with 0.447. So I've rounded that. 2 decimal places, 0.45, and the mark scheme allows gradients within plus or minus 0.2. So it's worth 3 marks, 1 for drawing the best fit curve, just nice smooth line through the points. Second mark for the tangent drawn at 50 seconds, so go up at 50, ruler touches the curve here, draw our tangent. And third mark for a gradient within this range. So that range is within 0.24 to 0.64. Next question, a student repeats the original experiment using the same amount in moles of barium as strontium. Calculate the mass of barium that the student uses. So since the moles are equal, we're going to work out the moles of strontium using mass over the mass number of strontium from the periodic table, and that will also give us our moles of barium. Then we can use the equation mass equals moles times mass number to work out mass of barium. And we come out with 0.41 grams. And to get our second mark, the question says give your answer to 2 decimal places. So part 2, the student observes the rate of reaction for barium is different from the rate of reaction with strontium. Sketch the graph the student would obtain using barium instead of strontium. So barium is lower down in group 2, that means it's more reactive. Therefore the rate will be faster with barium because it's more reactive, so the line will be steeper. We'll reach the same volume of gas produced but at a quicker rate. So the line's going to finish in the same place on the y-axis. So where do we get our marks on this part 2 where we're sketching on the graph? So we need a steeper initial gradient with barium and it needs to level off earlier, and same volume of gas produced, so it finishes in the same place. So here's the steeper initial gradient, it's levelling off sooner and it's finishing in the same place. Next we have to describe and explain the difference in reactivity of barium and strontium with water. So barium is more reactive than strontium because it's lower down in group 2. That means it has more electron shells, or we can say it has more shielding. Therefore, the nuclear attraction is weaker in barium. That means it's easier for barium to lose electrons, which is how metals react. This question we're given formation data, so that means we can either do a Hess cycle or we can use the equation products minus reactants. And we're using this balanced equation and these formation values, remembering to times our values by the number of moles, so 3 times the value for CO2, 3 times the value for H2O, and this one's 0 because it's an element. So we should come out with minus 2060, which is A. This one is about bond enthalpies, and it's asking us to calculate the bond enthalpy of the HH bond in this reaction. So we need to set up our equation. Delta H equals reactants minus products when we have bond enthalpies, or we can say breaking minus making. So delta H equals, I've collected the reactants, so we've got 4 CH bonds plus 2 OH bonds minus 3 HH bonds, that's what we're trying to work out, so I've called that X, plus this CO triple bond. Then we rearrange, collect our terms, divide X by 3, and we should come out with plus 432. And we know that's sensible because HH bond is a single bond and it needs to be similar in bond enthalpy to these, which it is. Here we have a practical based enthalpy of combustion question, and we have a table of data where we have to work out the mass of propane used, so mass of propane burnt, and the temperature change. So it's asking us to find enthalpy of combustion. First thing we need to do is Q, energy, equals mc delta T, and remember it's always the mass of the water or the mass of solution. So it's 100 times that constant specific heat capacity, which is on your data sheet, times our temperature change. And the answer comes out in joules because C is in joules. Then moles of propane, we can do mass over MR. Subtract these to get our mass burnt. MR is 44, and we come out with this amount of moles. To get enthalpy of combustion, we do Q over moles. We need to convert our Q into kilojoules, or we can do it after, as long as you remember it's up to you, because delta H needs to be in kilojoules per mole. And we come out with 1862. Now the reaction was exothermic because the temperature increased, so we need to give our answer a minus sign. And the question says it wants 3 significant figures, so this will become minus 1860. Another practical based question, it says the student's experimental enthalpy change is much less exothermic than the accurate one in the database. Suggest 2 reasons for this difference. So the first big reason is heat loss. So when you do a practical, there's a lot of heat lost in these kinds of reactions. And another reason is incomplete combustion of the alcohol. And that's something that happens when we don't have excess oxygen. And we often see evidence of that by soot formed. This is a very big question. There's a lot to look at. So it's a Hess's law one. We've got 3 reactions that are linked by a Hess cycle. So it says the student is carrying out an investigation to find the enthalpy change for reaction 1, but this cannot be found directly. So we're using reactions 2 and 3 to get reaction 1. So we have some data for reaction 2, and we need to do Q equals mc delta T, calculate moles, and then do delta H equals Q over moles. Then we can get our value for delta H2. And we're given a value for delta H3. So after we've calculated delta H2, we've got this one already. We can use this Hess cycle to find delta H1. So using this data then, let's get delta H2 first. So it says we're adding about 100 centimetres cubed of acid solution. But if you look here, we can calculate accurately the mass of solution by subtracting these. This is M that we're going to use in Q equals MC delta T. C is our constant again, specific heat capacity, 4.18, and delta T, we can subtract these and get 5. So here's the working for calculating energy for delta H2. We use the mass from the subtractions from the table times our specific heat capacity times our temperature change, and we come out with 2.1529 kilojoules. Then we find the moles of the limiting reagent. It tells us that the acid is in excess. That means the magnesium carbonate must be the thing that's limiting. So we use this mass over the MR of magnesium carbonate to get moles, which come to 0.05 moles. Then we can do Q over moles to find delta H. And our delta H is negative because there was a temperature rise. Now we have our delta H2 and we have a delta H3 that was given to us in the question. We can use our Hess cycle to find the unknown delta H1. So if we have a good look at this Hess cycle, we can see we have route 1 and route 2. So there are two routes going from magnesium carbonate to these products. We can go clockwise or we can go anti-clockwise. And Hess's law states that no matter which route is taken, the total enthalpy change is the same. So we can write that as route 1 equals route 2, and we can collect the terms involved in those routes. So I've called this one route 1, delta H2 equals route 2, delta H1 plus delta H3. So delta H2 equals delta H1 plus delta H3. Now we rearrange for what we want to find, delta H1. So we leave this where it is, we want it to stay positive. This is already on the opposite side, so we can leave that where it is, and we move this across the equals. So if delta H3 moves across the equals, it needs to change its sign from plus to minus. Now we can plug in our values. Delta H2 is minus 43.06. Take away our value for delta H3, which was in the question, minus 136.1. And we come out with plus 93.04 because two negatives make a plus. This is the last question and it's an extension question. We've got quite a bit of data again, like the last one, and the tricky bit is to find out where to start. So we have a table of bond enthalpies, and the question says the student determines the standard enthalpy change of combustion of propane using the bond enthalpies in the table. The bond enthalpies can be used to find the standard enthalpy change of reaction for equation 3.1. Then we're given an enthalpy change of vaporization of water. And that definition refers to 1 mole of water in the liquid form turning to 1 mole of water in the gas form. So to convert that delta HR to delta HC enthalpy of combustion, which is what we're trying to find, we need to get that water in the liquid phase, and we're going to use delta H vaporization for that. But instead of going from liquid to gas, we need to go from gas to liquid, so we need to reverse the sign of the enthalpy change. So I've circled what the question's getting at. We've got 4 moles of water in this one, 1 mole of water in this one. The place we want to start is use these bond enthalpies to find out the enthalpy change of reaction for this equation. So I've drawn out all the bonds involved in this equation so I can see them, and then I use the bond enthalpies from this table and plug in the terms. And I'm going to do reactants minus products, or breaking minus making. And we come out with minus 2054. The question is asking us to find the standard enthalpy change of combustion of propane using the delta HR value from equation 3.1 that we've just calculated and the delta H vaporization for water. So to do that, we need to look at the differences between these two things in terms of water and set up an equation to find enthalpy change of combustion.